Okay. Hi everyone. Thanks Juan for the introduction, and I also want to thank the organizing committee for letting us presenting this thing today here. We're super happy to do so because it actually started last year during the Grenoble workshop, and you've seen that this has grown a lot. We have several collaborators that actually here today. So yeah, I'm sure you are kind of aware of what is the state on the conversation about quantum energy right now. This is why we are here. But we know that there is this rising interest regarding this topic, but anyways, we still see that there is a huge lack of information regarding actual power consumption of real quantum devices. And also we are missing some benchmarking techniques and metrics to assess whether these computers are efficient or not, right? So we are trying to fill this lack of information. And in order to do so, we have contacted several collaborators for different qubit technologies mainly. I started this project with Rajay here that I met last year on the workshop. And for superconducting, we have people from Kilimanjaro, actually Jose is in the room, and Tesga. For spin qubits, Victor from ICFO, he's also here. For tap-times, we work with Gerard and Clara from the National Quantum Computing Center in the UK. Sophie from Harvard worked on neutral atoms. We have people from Candela, Ariane is also in the room, and Sam from ICFO. And then we have a section devoted to compilation, and we have colleagues from Telecom Paris and UPC that work on that section. Finally, these are my supervisors. Eduard is also here in the room. So yeah, these are the main topics or the main qubit technologies that we have covered in our paper. But basically, if you are interested in any specific platform, you can, like, I will refer to these collaborators, and we can talk during this year workshop. So the first thing that we realized talking with these collaborators is that these quantum computers display a flat power consumption. That means that even if you are computing or you're running algorithms in your computer, you see only a negligible spike of power consumption, right? So instead of building a model that was trying to assess the energy cost of each one of the operations happening during computation, like get execution, measurement, heat evacuation, etc., what we did is to build this component list for each one of the computers that we are studying in our work, on which basically we list all the basic components that one would need to perform computations on a given qubit platform. So this is an example of a spin qubit computer. And with this information in mind, the consumption of this computer would be just the sum over the whole list, basically, right? So this is based on measurements that our collaborators took, and also literature review. Right, so I already mentioned the platforms that we're covering, but basically we can identify three big families, which are solid-state computers. That contain superconducting and spin qubit computers, and atom-based computers that have trapped ions and neutral atoms, and then finally photonic, which we considered the Candela's architecture on-chip linear optics devices. Okay. So I will show some examples of the results that we got and the estimations that we got. I will focus mainly on solid-state computers, not because our work is focused on that. It's pretty balanced in terms of what platforms are we covering, but just for the time constraints, right? So this is an example of two power breakdown of two computers, which are in this case superconducting and spin qubits. The superconducting one, both of them range about 15 qubits. The superconducting one is based on data from Tesga and Kilimanjaro, and for the spin qubits, Victor helped us out. It's mainly, we took some information from the superconducting one, since they are fairly similar platforms, but also we did like a literature review on spin qubits. And as you can see, here we assumed, or we estimated rather, that these computers consume about 20 kilowatts of power, and we see interestingly, or as expected in fact, that the cooling, the power devoted to cooling the processor is actually the main power consuming part, and it consumes about 80% of the overall power. Right. So an important message that we want to convey in this work is the fact that more power consumption does not necessarily mean a computer to be less efficient, in the sense that if one has two computers, the first one consumes twice as much as the second, but it can perform 10 times more algorithms in the same time, one would rather to use the first one rather than the second, right? So in this context, we are introducing our figure of merit that we call the energy efficiency, which is basically the number of algorithms that a given device pi can perform in a given time, divided by the energy consumed by this device on this time, right? So we have already discussed power consumption. We assume it's flat. Therefore, the energy consumption of a device pi in a given time would be its power consumption multiplied by the time. Okay, this is easy. And then we go into what I think is the most intricate and interesting part of our work, which is to estimate how many algorithms a device pi can run in a given time, right? So this would be this time divided by the time to compute this given algorithm, and therefore one can write the energy efficiency of this device pi running algorithm A as 1 over the time to compute this algorithm multiplied by the power of the computer. So in order to characterize this energy efficiency and the time to consume, to execute these algorithms, what we did is to not choose specific algorithms to benchmark all the platforms, but instead we tried to describe or characterize all possible algorithms using a small set of parameters, right? So mainly we have two parameters that show up in almost every platform, which are the number of samples and the depth of the circuit. So an algorithm is actually a series of circuits executions on a device. So due to the probabilistic nature of quantum circuits, it's not enough just to measure your quantum state once. So in general, you would need multiple samples of your quantum circuit, even if you have perfect fidelity, right? So this is number of samples. And then the depth of the circuit. Well, a circuit is basically the representation of an algorithm using unitary gates that can usually be compressed together and be parallelized in different time steps. As you see here, this is an example of a circuit that has many gates that are compressed, and you can see that this circuit is executed in different time steps or layers, and then the depth of the circuit is basically the number of layers that the circuit has, right? So the time to compute an algorithm would be the time to compute this given circuit multiplied by the number of samples that you're taking, and then to estimate how much time do I need in a specific computer to compute a circuit is interesting, right? And it's what is the most interesting part in this work. So what we did is to, from all the platforms that we had, is to identify the main operations that are the most time-consuming ones, right? So this is an example for trapped ions computer. In this case, we identified 4 main operations happening during computations. We have reset, we have the measurement, transport, and most importantly, we have this clock time. So here we are assuming that these computers work on what we call a synchronous regime, meaning that we assume that there's an operation that is taking most of time during each one of these layer executions, and these layers will take the same amount of time, assuming that this operation is what is determining this clock time, right? So we have, like, each one of the layers needs clock time to be executed. So in order to do these estimations on the time to compute circuits in different platforms, we had to develop kind of different models for each one of the platforms. They are fairly similar, but have their own specific interesting parts, right? So basically for solid-state computers, this is the most straightforward model here. We identified 3 main operations, which are the reset of the qubits to the 0 state. At the end of the circuit, we have the measurement, and then, of course, we have the time to perform all the gates, which is the depth of the circuit times the clock time. Then we have, for atom-based computers, a fairly similar approach, but in this case, we are adding an extra term that accounts for the transport of the atoms inside of the computer. So in general, atom-based computers have different regions defined to store and operate with qubits. So if you want to perform some gates on a given set of qubits, you have to take these qubits, put them in the interaction zones, or the gate zones, as we call them, and perform these operations, right? So this term here, That's right. This term here accounts for the proportion of transports that you need to perform for a given circuit. And finally, for photonic computers, we have a completely different approach. Here, the circuit on a photonic device is not applied by a series of unitary gates, but instead we have this interferometer mesh that the photons are sent into, and this circuit, sorry, this interferometer mesh actually represents the overall unitary operator of the circuit. And this happens at negligible time because photons cross the interferometers at speed of light. So in this case, the time to compute a single sample of a circuit would be determined by the rate at which you can generate photons, right? So this rate source. And then these terms account for the probability of you losing a photon in this process. So you have a chance of losing photons, and therefore for measuring a single valid sample of this circuit, you have to perform several tries until you measure a valid sample. So I will show you an example or a couple of examples of how we display this information in our work. This is we plotted here the energy efficiency of a superconducting computer based on the depth of the circuit and the number of samples. So in the left panel, you can see how we have several series of energy efficiency for different values number of samples, which are equally spaced in the logarithmic scale. This is because the energy efficiency is always inversely proportional to the number of samples. But if we go to the right panel, we see that there's a different behavior for the depth. So in this case, for shorter circuits, we have these lines very close together. And this is because in superconducting computers, the reset and measurement time, which are operations that happen only once in a given sample, are 2 orders of magnitude higher than the clock time, which in this case correspond to the 2-qubit gate, right? So for short circuits, most of the time is consumed or is spent on resetting and measuring the qubits. And until you have not you have not increased the depth of your circuit enough, the clock time doesn't start taking over the whole computation. We have a very similar example here, but even more exaggerated for spin qubits computers of the same size. In the left panel, we see the same equally distant number of sample series. In this case, that means, similarly, that means that the energy efficiency is inversely proportional to the number of samples. But then for the depth series here, we see that even for light circuits that have between 100 and 1,000 layers, we see that the energy efficiency of this device is really similar. And this happens because the reset time of the qubits is really, really slow compared to the clock time. It's actually 5 orders of magnitude larger than the clock time. So even if you have a large circuit, all the time is consumed on resetting the qubits, and therefore there's no difference in energy efficiency executing these circuits of this size. Right, so another thing that we wanted to do with this framework is to use it to compare different architectural features or different technologies that can improve the energy efficiency of computers or are being relevant in these, for these platforms, for these specific platforms. This is an example for solid-state computers. As you might know, we have this connectivity constraint where the processor or the qubits in the processor are connected in a limited way that can be often presented like these connectivity graphs, right? So if I want to perform a 2-qubit gate between qubits that are distant in the graph, I have to place a bunch of swap gates in the middle in order for them to be connected by an edge, right? So that means that a given circuit, when it is compiled for a processor with limited connectivity, will increase in depth. And if it increases in depth, then the computing time of the circuit would be larger, and this affects the energy efficiency, and the energy efficiency drops due to this overhead of depth, right? So in order to characterize this, we have included 2 parameters in the model, which are the ratio of layers with 2-qubit gates, and then this average shortest path length of the connectivity graphs that basically tell you how many, on average, how many swap gates they have to put between distant qubits. So this is a comparison between different spin qubit architectures. In this case, we have included 4 spin qubit architectures. A spin qubit device that has a linearly connected processor, another that has a square lattice connected processor, and these two extra architectures that we call the crossbar. I don't have time to go into detail about this, but they are mainly focused on reducing the power consumption of the electronics thanks to multiplexing of the lines. But for the linear versus the square comparison, we basically can see how if we increase the pre-routing depth of the circuit, the scaling of the linear processor is worse than the square processor. And this is because for the same original circuit, after compilation, it will have extra depth for the linearly connected processor, and therefore the energy efficiency of this processor resents. Right? We did similar comparisons between interesting technologies for the other platforms. Mainly for superconducting, we have compared active versus passive resid technology. For trapped ions, we have compared devices that have multiple gate zones, and therefore the parallelization of the circuits is different. And then for neutral atoms, we have compared the periodic versus the continuous reload technology that reloads the atoms into the register. And finally, for photonic, we have compared materials on the interferometry mesh. So as a conclusion, we've been able to display actual consumption of power devices. And we have seen a trend on consuming more power for the current size of quantum devices to consume more power on ensuring the proper environmental conditions for computations. We have developed our own method to assess the energy consumption and efficiency of quantum devices. We have delivered these estimations for the devices that we were considering, and we use this framework to compare specific technologies that can improve the energy efficiency of these computers. With this work, we are not trying to compare platforms face-to-face, and we are aware that they are on different stages of development, so we're not trying to assess which one of them is better for computation in general, and actually we expect that some algorithms can be run more efficiently in each one of these platforms, right? And in the future, we would like to also include fidelity into this model, which brings me to the next future iteration, which is basically performing the same kind of analysis for quantum error correction codes. And of course, we understand that this methodology can be extended to other computing schemes or other qubit technologies like MV centers, quantum machine learning, annealing, etc. So that is the end of my presentation. Of course, this paper was actually published last week. If you are interested, please check it out. It's on archive. Thank you so much.
Thank you. Thank you for the talk. Yeah, it was interesting, and I have a question actually that is probably related to the last point. Mm-hmm. So for instance, if I take this way of benchmarking, you essentially compare the speed of the computer, the number of algorithms I can do. But the thing that to me could be an issue is that indeed if there is no fidelity in the estimates, you could say that this computer is so much better because it can run 10 times more algorithm, but it's actually a random number generator compared to the other that is much more accurate. So yeah, how do you envision taking into account fidelity, for instance?
So yeah, that's like an important topic for sure. We are not 100% sure on how this would fit into the model straightforwardly, but I think when considering quantum error correction, this fits more naturally into the model. Now fidelity is directly related to the number of qubits that you have. It's also related to the time because you're executing this measurement and this syndrome extraction, whatever. We have the intuition that we could account for fidelity in the number of samples, but we are not sure. But anyway, since our first approach was to be able to do this analysis for a lot of technologies at the same time, for mainly time constraints, we couldn't extend this work any further. But it is something that has to be introduced here at some kind.
And just a last quick question. There is also something you consider a gate set. So you want to run a given circuit, but one platform might have a gate set, so that with a given width and depth of the circuit, if a platform has much more native gates, you could do much more things So how is this taken into account?
Right, this is not taken into account because what we do is characterize circuits depending on their post-compilation depth, right? So we have some discussion in the paper where we compare how some circuits might grow depending on the basis gate of, as you said, like we see different depths of circuits depending on the gate set. So that means that if you take a circuit of a given depth for a platform and you go into another platform, the depth that you can expect for this circuit to have is completely different. And this is why we cannot compare platform face to face also. But yeah, this is some analysis that could be done, right? For a given computer, let's say I have two gate sets, and then I want to compare the energy efficiency of this device with these two gate sets. This is something that can be done. Right.
One last.
So very nice. One question I have maybe for you, which is an experience I have with trying to build models similar to this, is sometimes there is no information about the thing you need to know to build the model in the literature.
Yeah.
So I see you have people from the companies as authors, so I guess my question is, if you had a wish list of information that you wished that companies would give you so you could build this sort of model,
okay.
Are there one or two things on that list, or did you basically find all of the information you needed?
Okay, so definitely one issue that we had is that with our collaborators, there was sometimes like they are not monitoring all the consumption of all the components separately. They have maybe seven different sources of power, and then like each source of power is in charge of half of the components, let's say. So definitely more detail on that regard, and also some kind of, I don't know how to say it, like we are not considering scaling in our work, and we have little information on how some components will scale. So maybe some more information on how that will happen. So for instance, we don't know if we increase the amount of qubits to a certain amount, how the size of the cryostat changes. So these two pieces of information are really valuable. Yeah, indeed.
Okay, thanks again, Miquel.
Thank you so much.